Welcome back, everyone, to the Deep Dive, where we do a deep dive into some really fascinating research. And today we're looking at a paper all about using reinforcement learning and, really focusing on what these systems actually see to build safer autonomous systems. And, think about self-driving cars, robots working alongside humans. I mean, the applications here, they're huge. But when these systems make mistakes, the consequences, they can be pretty serious.
Yeah, absolutely. As reinforcement learning moves beyond those really controlled environments and into these like real world scenarios where, safety is absolutely paramount. I mean, it's not just a theoretical concern anymore, right? We need really robust ways to evaluate and make sure that these systems are safe. We've already seen how powerful RL can be for complex tasks, but ensuring these agents are, operating reliably and not, causing harm in unpredictable environments. So that's a real challenge.
And that's exactly where this research comes in, right? The paper really highlights this gap in how we currently assess the safety of these vision-based RL agents. Like a lot of the existing ways of testing these systems, they just aren't, they just don't cut it. Some are too simple, operating in these very artificial 2D worlds. Others just rely on data that a real-world agent would never actually, see. And then the ones that are more realistic, like using 3D environments, they're often so computationally expensive that it becomes almost impossible to do really in-depth experiments.
Yeah, it's a tough problem. I mean, we really need better tools to develop and test these safety mechanisms for systems that are learning directly from what they see, and real-world safety. I mean, it's not just some abstract concept, It's about preventing accidents, avoiding damage, and making sure these things work reliably in these very complex environments that they need to visually understand.
So this paper, it introduces this benchmark called HASARD, which stands for Harness Safe RL with Doom. Yes, Doom the Ilana, the video game. Now, before you get any images of, pixelated demons in your head, this is all about, leveraging the VizDoom platform in a very new and clever way. They've created these 6 brand new 3D tasks specifically designed for pushing the boundaries of safe reinforcement learning. And the key here is that it's all using egocentric vision, so it's like that first-person view, the same way that we see the world.
Yeah, the use of VizDoom here, it's a really strategic choice. It's known for being incredibly efficient, and that means they can achieve some seriously high simulation speeds. I mean, we're talking potentially tens of thousands of iterations per second, even on standard hardware. And this speed, I mean, it's not just a nice bonus, It fundamentally changes the scale at which we can, do these experiments in safe RL. And then by focusing on egocentric vision, HASARD, it's really targeting how these agents learn to, navigate and make decisions about safety based on what they actually see. And that's so crucial for real world systems.
So our mission for this deep dive is to understand how exactly this new benchmark, HASARD, can really push the field of safe RL forward. So let's get into it. What are the really key contributions of this paper?
Well, at its core, the paper introduces HASARD as this response to the limitations of the current benchmarks out there, especially for agents that learn from visual data. I mean, they saw that while safe RL has definitely, made progress, there just weren't any good tools to test how well agents could learn safe behaviors in these complex 3D settings. Tools that were both robust and computationally efficient.
And that's so important, right? HASARD, it's not just about throwing together some new virtual environments. Each one of these 6 tasks is designed with safety as the core principle. So, for example, you have armament burden, where the agent has to collect weapons, but has to manage how much it's carrying. And if it goes over the limit, that's a cost. So it's not just about grabbing everything in sight. It's about making those strategic and safe decisions about what to carry.
Yeah, and then you have remedy rush, where the agent has to collect these health items while avoiding anything harmful. So this one really emphasizes the agent's ability to tell the difference between what's good and what's bad in the environment, visually, and to move precisely to achieve that goal safely.
And collateral damage. Now, this one it's a really tactical challenge. The agent uses a rocket launcher to eliminate targets, but it has to be extremely careful not to hit any neutral units that are nearby. I mean, the blast radius of the rockets. It means it has to aim very accurately and really understand the spatial relationships between things so that it can avoid any unintended, consequences.
Right. And then there's volcanic venture, which is all about navigating this really dangerous environment. The agent has to move across these platforms over lava to collect items. And of course, if it falls in, there's a coast. This one really highlights just how important depth perception is for safe navigation, using only visual input.
Precipice plunge is a really cool one. It involves descending this treacherous cave, and any falls, well, they lead to some pretty big health loss. And the paper even mentions this like limitation in the game engine itself that makes it even harder to judge distances visually. Figure 13 in the paper actually shows this visual distortion, which is it's kind of unexpected.
Yeah, and lastly, there's detonator's dilemma, where the agent has to detonate these explosive barrels, but has to make sure that neither it nor any neutral units get hurt. And the interesting thing here is that these neutral units, they patrol the area on these predefined paths. Figure 9 shows what these paths look like. So it was like this element of predictable movement that the agent can actually learn to visually anticipate and use that to plan safe detonations.
Wow. So HASARD, it really presents this diverse range of challenges, and they all come down to learning safe behaviors from that first-person visual perspective.
It does. And it's these key features that make HASARD really stand out. First, you have the variety of tasks, right? It really tests a wide range of safe RL capabilities. Then you have the fact that unsafe actions always come with a cost, and these costs are avoidable. So it really pushes the agent to learn genuine safety, not just figuring out how to minimize penalties. The whole thing is based on egocentric vision, which really reflects how these things would work in the real world. And it's computationally efficient enough that we can do some serious research with it.
Yeah.
And of course, they even provide simplified action spaces so that researchers can really focus on those core principles of safe RL. And the fact that it's open sourced with baseline implementations, I mean, it makes it so much more accessible to the research community.
And we can't forget about the different difficulty levels. That's a really smart design choice because it means that HASARD stays challenging even as our algorithms get better, right? It's like this built-in way to measure progress over time.
Right. It's constantly raising the bar. To really get why HASARD is so important, I think we need to understand just how reinforcement learning has evolved and why safety has become, so critical. I mean, RL has come a long way. It's gone from, these theoretical concepts to actually solving real world problems in fields like transportation traffic management, optimizing energy usage and of course developing these autonomous systems. And look at what RL has done in gaming. I mean, we have agents that are playing at superhuman levels. So it clearly has massive potential.
Definitely. I mean, if we look back, early RL research, it was mostly about getting high rewards in these fairly simple and well-defined environments. But as we started to apply it to, real world problems, especially in areas where a mistake can have serious consequences, it became obvious that we had to build in safety. A mistake in a game, it might cost you some points. A mistake made by a self-driving car, that could cost lives.
Yeah, exactly. And that need for safety, that's what led to this whole subfield of safe reinforcement learning. Early on, people were trying to adapt existing RL environments by adding in these safety constraints. Or they were designing these simplified 2D environments to study the basics of safety. And there was a lot of work done on making robotic manipulation safe, but that often relied on data about the robot itself,
right.
like its joint angles or sensor readings rather than what it was seeing in the environment.
And that's a key difference with HASARD. It's a focus on embodied learning from that first-person visual perspective. I mean, it directly addresses the needs of applications like autonomous driving, where the car has to see its surroundings and react safely, right? Or robots that work in environments with humans, or even UAVs that have to navigate these visually complex landscapes. In so many real-world scenarios, vision is that primary source of information.
And the paper does a nice job of comparing HASARD to some other safe RL benchmarks. Table 1 lays it all out, things like AI Safety Grid World, Safety Gym, Safety Gymnasium, and Safety Vision. And what stands out is that HASARD has this unique combination of features. It's 3D, it's got multiple difficulty levels, it uses vision as the main input, it's got stochasticity built in, it's computationally lightweight, and it features partially observable states, which means the agent only sees what's in its field of view at that moment.
It's worth mentioning safety vision specifically. While it does have those 3D environments, the authors point out that it doesn't really take advantage of the physics engine to create, truly realistic tasks. And a lot of the challenges, they can kind of be reduced to 2D problems with hazards that are either static or predictable. HASARD, on the other hand, I mean, it has these dynamic environments and the agent has to reason about space based on what it sees. So
Right.
It presents a very different and arguably a more relevant set of challenges if we're talking about, building systems that are truly safe.
Absolutely. And the authors also mentioned how they were inspired by earlier benchmark research and how they specifically chose VizDoom because because of its flexibility and really its speed, they clearly prioritized being able to run a large number of simulations, which is essential for RL research, even if that meant, accepting some limitations in the visual realism or the complexity of the physics.
Okay, so we've got a good understanding of what HASARD is and why it's important, right? So now let's dig into how some of the standard RL algorithms actually performed in this benchmark. The paper tested 6 different baseline methods.
Right. So they looked at a whole range of algorithms. They started with PPO, which is sort of a basic baseline that focuses on maximizing reward without really considering safety costs. Then they look at PPO cost, which just treats those safety costs as negative rewards. PPO lag, that's a more dedicated safe RL approach.
Yeah.
It uses Lagrangian optimization to try and keep the agent within those safety limits.
Yeah.
PPO saute tries to incorporate safety by augmenting the state.
Yeah.
PPO PD that uses a PID controller to try and balance, going for rewards with sticking to the safety rules.
Mm-hmm.
And then finally, there's P3O, which combines aspects of PPO with these off-policy corrections.
And the results, which are summarized in Table 3, they give us some really interesting insights. As you might expect, PPO, it got the highest rewards overall, but it completely ignored the safety costs. And that really shows you how dangerous it can be to just focus on performance, especially in situations where safety is critical. PPO cost. Well, it did show some balance between rewards and costs, but it couldn't guarantee that the agent would stay within those acceptable safety levels.
What's really interesting is how the algorithms that are specifically designed for safe RL performed.
Mm-hmm.
So PPO lag. It generally managed to stay within those safety boundaries, but it often did so by getting much lower rewards compared to that unsafe baseline, PPO saute and P3O. They sometimes went over those cost limits, although P3O did get higher rewards in certain cases.
But the one that seemed to do the best overall was PPO Pi. It consistently stayed within the safety constraints, and it often got the highest rewards out of all the safety-focused methods. So this suggests that its approach to balancing reward and safety, in this dynamic way, it's really well suited to the types of challenges that HASARD throws at it.
Yeah. The researchers also wanted to see how changing the strictness of those safety limits impacted performance. And Figure 4 shows what they found. It's not surprising, but as they made the safety limits stricter, the rewards generally went down. And that really highlights that fundamental trade-off between maximizing performance and ensuring a high level of safety.
And one of the really cool findings is in Table 4. It shows that HASARD might actually have this sort of built-in learning curriculum because of those different difficulty levels. They found that training agents across those progressively harder versions of the environments led to big improvements in the final performance. This was especially true in remedy rush and collateral damage when they used the PPOP algorithm. So it seems like starting with the easier versions of the tasks can help the agent learn these fundamental skills that it can then apply to those more complex and demanding scenarios.
Yeah, that's really neat. It speaks to the value of having a well-designed benchmark where the structure of the environment itself can help with learning. It's not just about how well the agent does on the hardest task, The whole journey through those different difficulty levels plays a really important role.
They also looked at what happens when you give the agent more information about its environment than just those raw RGB pixels, Figures 5 and 6 show the results of experiments where they used segmentation masks and depth buffers.
Right. So in the armament burden environment, when they gave the agent segmentation information, basically a labeling of what each pixel in the scene represents, well, it made learning much easier, and the agent was able to collect more rewards and precipice plunge. Giving the agent access to a depth buffer, which tells it how far away things are, that turned out to be critical for navigating safely, and the rewards increased dramatically. It really shows how difficult it is to figure out spatial relationships just from those raw pixels. And that giving the agent these extra visual cues could be incredibly helpful for learning safe behaviors in certain environments.
And finally, the paper uses these heat maps, which you can see in Figure 7 too, to show how the agent is actually navigating during training. They give us this visual way of understanding how the agent explores its environment and how it learns to be safer over time. It starts with random exploration, and then it starts to move in a more focused and cautious way. Appendix C.5 has some more examples of these heat maps, including a comparison of the strategies used by different algorithms in precipice plunge, and an analysis of how the difficulty level affects exploration and armament burden, which which is shown in figure 18.
Yeah, those visualizations are really useful. They let us go beyond just looking at the numbers. We can actually see how the agents are solving the tasks and whether they're really learning those safe and efficient strategies.
Of course, the authors do acknowledge that there are limitations to using VizDoom. It has its advantages for sure, but it doesn't perfectly simulate real-world physics or visual fidelity.
Right. VizDoom is great for rapid experimentation, but it can't capture all the nuances of real-world physics, the kind of things you might find in a dedicated robotics simulator. And using those discrete action spaces. I mean, it helps to focus on those safe RL principles, but it is a simplification compared to the continuous control that you often need in real-world applications.
Looking ahead, the paper suggests some really interesting directions for future research. They talk about incorporating multiple safety constraints at the same time, developing benchmarks for multi-objective tasks where agents have to balance competing goals, creating these collaborative multi-agent scenarios where multiple agents have to work together safely, and even exploring continual learning or transfer learning using that full action space that's available in VizDoom.
Those are some really cool ideas. I mean, those extensions would make HASARD even more valuable and really push safe RL research in some exciting new directions.
And now it's time for our novel notions segment, where we take the research a step further and brainstorm some potential applications or extensions that build on this work.
Okay, so given how incredibly fast HASARD can run these simulations, imagine using it to train a generative adversarial network, a GAN, that's specifically designed to create new safe RL environments within that VizDoom framework.
Yeah.
So the generator part of the GAN would be, coming up with new layouts and safety challenges, and the discriminator part would evaluate how well those generated environments actually test the safety of the RL agents.
Wow. So instead of researchers having to manually design these new benchmark levels, we could have an AI system that just automatically generates this ever-evolving set of increasingly complex safety challenges.
Exactly. And then the data that we collect from training agents in those AI-generated environments, especially the data from when those agents fail, well, we could use that to make our safe RL algorithms even better. It would be this continuous loop. The AI generates new challenges, the agents learn, the algorithms improve, and it just keeps going.
I love that idea. Okay, here's another one. What if we used HASARD's ability to do visual segmentation and provide that depth information, but not to train end-to-end control policies for real robots? What if we used it to train more robust and interpretable perception modules that are specifically focused on safety?
Can you elaborate on that a bit?
Sure. So instead of trying to take the entire control policy that an agent learned in that Doom environment and directly transfer it to a physical robot, we could focus on teaching a perception system how to reliably identify hazards and safe areas from, the messy visual data that it gets in the real world. Imagine a robot working in a warehouse where things are constantly moving. It needs to instantly recognize obstacles and identify where it can drop things off and maybe even anticipate how humans are going to move.
So instead of learning actions, it's learning to understand the visual scene in terms of safety.
Exactly. And then these learned perception modules, which maybe we could build using things like graph neural networks that can understand how objects are spatially related to each other. Well, we could then integrate those into existing robot control systems. And that would give them this extra layer of safety awareness that might be more reliable than relying on just end-to-end RL, which can sometimes learn solutions that are kind of brittle or hard to understand. It's about building that foundational understanding of safety in a way that can be applied more broadly.
Yeah, that's a really compelling thought. It's like shifting the focus to transferring that safety awareness through these perception modules. It could be a much more modular and potentially more reliable way to build safe autonomous systems.
I think so too. And on that thought-provoking note, we'll wrap up this deep dive into HASARD. You can find a link to the full paper in the show notes if you want to learn more. And be sure to join us next time on the deep dive as we unpack another fascinating piece of research.